Yeah, thank you. So in this talk, I want to start by giving a bit of a teaser. I know it's almost lunch, so I don't want to make it too technical. So Agda accepts the following functions that Rock doesn't. So this first function is just addition. However, in the recursive call, I've swapped the two arguments. So this is, of course, it should give us the same function because addition is commutative. However, the computation rule is different, and it's not immediately obvious how you make this with your normal induction rule. And the other function is this one, which calls itself twice. And the argument that it calls itself on is either coming from the first or from the second one. So the question is, why do these functions terminate? And can we define them with our normal induction rules? So the starting point, so the overview, is that we're trying to connect a field called cyclic proof theory with the ways that recursive functions can be defined with pattern matching and co-pattern matching. So in this cyclic proof theory, we don't add induction or co-induction rules, but instead we add some kind of circular reasoning, which sounds very scary, but we can still make sounds. So for example, suppose that we're working with arithmetic. Addition is now just a normal one, recursive on the right. And we want to show that adding 0 on the left is also the identity. Here we can first do a case distinction on x. And then in the successor case, we eventually reach a goal that's very similar to the one that we started with. So here we can allow a cycle between the nodes. And this proof is valid because we make some amount of progress before we cycle, namely the number has become smaller. So one of the motivations for cyclic proof theory is that it's very good for proof search. So instead of having to guess an induction or co-induction rule, you just start generating a proof until you see something, a goal that you've seen before. And then you check that you've made progress in the meantime. And the way the type theory is implemented by proof assistants can be seen as a cyclic system in such a way. So this is an extension of the Curry-Howard correspondence. So inductive and co-inductive types, they generalize fixed point formulas. And a recursive call in a function is one of these cycles in your proof. And then termination checking corresponds to the soundness condition that we have to put on these proofs. So I have two main goals in this project. First, explain how this Curry-Howard correspondence extends. But then also we want to extend current conservativity results. So we want to show that the proofs that are accepted can be implemented with a normal induction rules, which means that they are valid in every model of type theory. Both with and without axiom K. So let's look a bit more at the soundness condition for such a cyclic proof. Because this is like the main thing we have to specify for such a system. We want it to be, on the one hand, restrictive enough to be sound. Of course, we cannot allow every cycle. But we also want it to be admissive enough to be complete and easy to use. So the more proofs we can accept, the easier it is to use your proof system. And this is called the soundness condition. With respect to a semantics that we have in mind. So I'm really trying to be very general here. So you have a lot of different proof systems that are cyclic in this way. And still trying to be very general, a condition you can often impose is called a global soundness condition. So this is where we can eventually trace an object that makes progress infinitely often. And both of these green things in the sentence really depend on the specific proof system. So if we look back at this example for arithmetic, then the objects would be variables and progress is passing through a case distinction. And in general, even though this is talking about infinite paths, this turns out to be decidable and piecewise complete. So cyclic proof systems generally fall into two different styles. on the one hand, we have systems where the sort that we're working with is inductive or co-inductive, such as natural numbers or ordinals or streams. And on the other hand, we have systems where the formulas themselves contain certain fixed points. So, for example, we can define the reflexive transitive closure of a relation to be the smallest fixed point of this equation. So it's the smallest relation satisfying this by implication. So we want a system that generalizes both styles. And then, of course, dependent type theory is a very natural choice because types can be seen as both sorts and formulas. So here we can have a system that combines both ways of doing cyclic proofs. So what are cyclic proofs in type theory? So the general idea is that a sequence can be seen as some sort of function, sending the context to term in the type. And then a cycle in this sequence, or cycle in the derivation of the sequence, would be using the function inside of the definition of the function. So a recursive call. And this is the way that we're used to working with proof systems. And then to ensure termination, we need to put some conditions on these functions. So for ROC, this is structural recursion. And the proofs that show that pattern matching can be reduced to primitive eliminators, they also deal with a structural recursion. So this can both be done with and without XMK. Whereas ACTA uses a more general principle called size change termination. And here conservativity is not yet known. So these conditions are sufficient, but of course not necessary because this is the halting problem. We cannot have both. So for structural recursion, we want one input to be structurally smaller in every recursive call. So for example, in this Fibonacci function, the function calls itself twice, and both times the argument is smaller. Whereas for size change termination, we have a condition saying that for every infinite sequence of calls, we eventually have a path that decreases infinitely often. So let's look back at our starting example. So this swapped addition. Here we can consider its call graph. How does it call itself? And here you see that the arguments swap. One of them we decrease, and one of them stays the same. And you can see that every infinite sequence, if you start combining this graph, has a path where we decrease infinitely often, in fact, every path. And this other example, here the function calls itself twice. So we have two different call graphs. And in both, we make progress in this way. And here you can also see that any way we can compose these squares in an infinite sequence, we will be able to find a path that decreases infinitely often. So this condition, this corresponds to this p-space complete global soundness condition in cyclic proof theory. And in cyclic proof theory, there are results showing that in some cases, this is conservative over induction. So a lot of these proofs are very semantics. So you really prove soundness and completion with respect to a semantics. But we are interested in the one that are a bit more proof theoretic, because those would be able to combine with the existing type theoretic proofs. So in particular, this is the work by Sprenger and Dam for the first order Moog calculus with ordinal approximations, and then also more recent work by Ley and Ware that use a very proof theoretic technique for this. And our goal is to prove a similar result for type theory. So one complication in type theory with respect to other cyclic proof systems is that we need unification to even specify what our cyclic proofs are. So if we're dealing with not only inductive types, but inductive families, then unification starts playing a role. So for example, if we use normal unification algorithm, then XMK is provable. So if we want something that's conservative over type theory without XMK, then we need to restrict unification. So this is really already present in what do we count as a valid cyclic proof? So for this conservativity, we're trying to combine ideas. So on the one hand, from type theory, we can get ideas how to deal with this unification and how to deal with whether or not we have axiom K. And then cyclic proof theory gives us some ideas for how we can deal with this global soundness condition. So the main idea that we're working with now is that we have to unfold the definitions a bit to get it into a shape that's easier to reproduce in an inductive proof. So for example, for this swapped addition, if you just unfold this definition once, instead of this recursive call, you just copy the definition again. Then you see that the arguments swap back around. Now it's a bit easier to work with. And for this definition, the existing constitutivity results would already show that they can be reduced to inductive proofs. And for this other example, it's a bit more complicated. So here we can consider the tree generated by composing these two graphs. And here the idea, the insight would be that in one side of the tree, we really only see our first input. And on the other hand, we only see the second input. So here we can unfold the definition, treat both cases not as a binary function, but as a unary function, and then match it with induction rules. So we have an algorithm to determine how much we should unfold the definition. So the idea is that we start unfolding and we add some kind of annotations. So these annotations are based on the Safra construction, which makes non-deterministic infinity automata deterministic. And if these annotations start repeating, then we can stop. So this gives us a process to unfold precisely how much we need, or maybe a bit more. And with these additional annotations, we can switch to a more local version of the soundness condition, where we don't have to consider the entire tree. We only have to consider the path between the two nodes that we're looping between. And then the annotations should also give us an idea of the order in which to imply induction. So we cannot do only a single induction here anymore. We need to do induction multiple times. And the annotation should give us some idea of which order we have to do this in. And this is where it starts to become a bit more speculative. So by following these annotations, we should be able to add induction hypothesis to the proof. And then instead of doing a recursive call, we should be able to use the induction hypothesis that's now present in the context to get a value of the type that we need. So to summarize, the Curry-Howard correspondence extends to recursive functions and cyclic proofs. And there are some methods of the cyclic proof theory that can be useful also in the setting of type theory. So ACTA admits more than ROC at the moment. We don't yet know whether it's conservative. And this is something that we're trying to prove. So our approach is a bit more general than what I've shown in this talk. So in particular, we can deal with arbitrary inductive families, which is where a lot of the complications come in. If you have to deal with more than just natural numbers. And also deal with a mix of different inductive families. And we can also do mutually recursive functions. So functions can also call each other. And then in future work, it would also be very interesting to look at co-pattern matching, because there are some cyclic proof theory techniques that can deal with this. However, yeah, this is far future at the moment. Yeah, and then my last slide is just some literature. So thank you.